start by thanking the organizers for giving me this opportunity to talk here and also for organizing this conference in this beautiful place. So this work was done in collaboration with Michael Abbott, János Balog, Árpád Hegedűs, Said Sadayan, and István Vona. And you have seen we published plenty of papers, and then we started to publish it in 2000. So it started as a...
Started in 2000, still haven't finished.
Yeah. It's haven't finished. I mean, maybe more are coming, but the point is that it started during COVID, and it started as a COVID hobby, and it seems we got so addicted we cannot finish it. So it's very interesting. And then, in this first very dense slide, I would like to connect to the observable we are calculating to the topic of this conference. So, which is beta ansatz. So imagine we are in one dimensions, and then we just put on the circle n particles, and there is a beta ansatz system, so there is a momentum quantization, which means that if you bring a particle around, you pick up the translational phase and also the scattering phases, and depending whether you are in a relativistic world or in a Galilean world, then your S matrix depends on the difference of that rapidities. And what we are analyzing is what happens if you put many, many particles and you send volume to infinity. So we would like to calculate the ground state, and in the ground state, this S matrix at zero rapidity is -1. So they behave like fermions, so they cannot occupy the same state, so you just densely fill the vacuum, and you would like to calculate the ground state energy. So the variable you would like to calculate is the rapidity density of these particles, and you determine this rapidity density just taking the logarithm of the beta ansatz equation and then going to the thermodynamic limit. And as a result, using the logarithmic derivative of the scattering matrix, you got a linear integral equation. And then you could say this is the end of the story. This is the ground state energy. I could calculate the density of the particles. I could calculate the energy corresponding to this ground state, and I could express the energy as a function of the density, and I know everything. So from the beta ansatz point of view, this is end of the story. But from my point of view, actually, I would like to solve this equation, this linear integral equation, and I would like to expand it perturbatively. There is also a large class of models where a similar equation appears, namely integrable quantum field theories, even very complicated integrable quantum field theories when you have some non-trivial global symmetry and you have a multiplet of particles and they scatter non-diagonally, and you would think the ground state energy is very, very complicated. But following the idea of Polyakov and Wigner, if you take a conserved global charge and then you couple an external field to this charge, then in the vacuum you can actually suppress all other particles except one. So even in this very complicated integrable quantum field theories, if you choose a good charge such that only one type of particle has a negative charge, then this negative charge particle, because you shift the dispersion relation, will condense into the vacuum. So the ground state in the presence of this magnetic field will be described by the same integral equation, and this k will be the logarithmic derivative of the S matrix. For example, in the ON nonlinear sigma model, the S matrix of the condensed particles is just this very complicated form, where this delta is related to the n of the ON model. We like this ON model particularly well because it is similar to QCD. So it's similar in the sense that it's asymptotically free in perturbation theory, and also there is a dynamically generated scale. Okay, so that's the motivation.
So you mean that even though there is a global symmetry, for this particular observable, you only have one integral equation?
Yes, and it's linear. So it's not like the usual thermodynamic beta ansatz, although we call it like a thermodynamic beta ansatz, but it's more like the thermodynamic limit of the beta ansatz, and in the statistical sense it's basically zero temperature, just a completely filled ground state. So I would like to solve today a mathematical problem which is slightly more general than the one I showed you, which has also parameter alpha here. So it's not just cosine theta, but cosine alpha theta, so this integral equation. And I would like to calculate generalized observables when I take this generalized momenta with cosine hyperbolic beta theta. And I will show you in my talk that you can expand in V-coupling. V-coupling expansion means B goes to infinity. So you can expand in 1 over B perturbatively. And you will see that actually, additionally to the perturbative correction, there are non-perturbative corrections, which goes like e to the minus B. So the full observable, the result of this solution of the integral equation and performing this integral, will be a double series, a series in the non-perturbative parameter, and additionally a series of the perturbative parameter. And I would like to show you how you can calculate all these coefficients at the end of the talk. There are going to be two differential equations which are very useful, and I will refer later to them as differential equations. And these differential equations actually relate all these generalized observables to one of them. Because if you take a look, you can take just the energy density, which is O11. You can plug with this equation, and you see the derivative with respect to B, this parameter appearing here, of this observable, which I will denote just by a dot, can be written as a product of the boundary values of this unknown function in the integral equation. So if I take O11, I can calculate this chi1, say, as the boundary. And then there is this other differential equation, which is also nice because the left-hand side depends on alpha, but the right-hand side doesn't depend on alpha. So taking just chi1, I could calculate this master function, say. And from the master function, I could calculate any other f chi alpha, and by integrating, I could calculate this O alpha. So basically, I have just one unknown O11, from which, using this differential equation, I can express all the other observables. So a similar integral equation appears in many other contexts, and let me just list a few of them. So I already mentioned that there are these two-dimensional integrable quantum field theories coupled to a conserved charge, in which case the observable is the energy density, is O11, and the density in this form is basically O10. These are the basic densities. And for example, in the O and sigma models, the S matrix is written in terms of this. I put it explicitly here because today, in most of the talks, I will talk about the O and sigma models, sometimes just O3 or O4. Okay, but you can, all this machinery generalizes for the n equals 1 supersymmetric extension of the same model, or to the O-N Gross-Neveu model, the SUN principal chiral field. They can be also described in the same way. In particular, the SU2 principal chiral field is just the O-N O4 sigma model, what I will talk about. In the case of the O3 model, some magic happens, and the kernel, what you calculate from this S matrix, it's just a rational function. And this is the same kernel what appears in the Lieb-Liniger model and also in the Godin-Young model. So what I will solve here will solve also these two other statistical physics.
Godin-Young, you have two of them, no? With two different scales.
Two different signs, you mean?
Godin-Young, you mean the
free fermion with a delta potential.
Yeah, but with fermions, right? And then you have two coupled equations, and this tonality appears in with two different scales.
Okay. Yeah, I think it's just one component what I'm thinking of. Okay, and there is also a very interesting classical electrodynamics problem, namely the capacity of coaxial disk capacitor. You just take two disks, coaxial, put the same charge or opposite charge, and you would like to calculate the capacity as a function of the ratio of this geometric data, d as the distance and a as the radius. So b serves as this dimensional radius, and in this problem, the observable, what we are interested in, is in this O00. Well, this is a classical problem. Why it was interesting? It was historically interesting because many famous people actually tried to calculate and they failed. So you will see it's a difficult problem actually to expand the integral equation. So this is the plan of my talk. So some part will be quite general for generic ON, some of them just for O4 because it's simpler. O3 is particularly interesting, and I will comment on this. And also I will make the general result at the very end for ON. Okay, so first I will give the definition of the model, then in two ways, the Lagrangian way and also the integrable way, and I will show how we expand the TBA, how to get the perturbative coefficients. And the last of the talk, maybe the middle part of the talk, will be the analysis of this perturbative series. And then that part goes under the name of resurgence, because these perturbative coefficients will grow like factorial. And then we should understand what to do with such a series. And then that's I will explain in detail in these particular examples. And then, yeah, the main question, maybe what I could raise now, if I know the perturbative series, does it determine completely all the non-perturbative information? And then what you will see that in the O4 model, it completely determines actually. And I will explain how you can extract all the non-perturbative information. But we will see that in the O3, it doesn't determine. So it's also interesting. And then using really the integral equation, I will show how to solve actually exactly in the sense that I calculate all these CNM coefficients.
So if you would have, how it's called, if you would have non-isotropic, so it will be not b and e2 minus b, but rather two powers, yes? 2 powers of b, right? Mm-hmm. I think so.
No, here I have only one power.
No, but if you are anisotropic, if you have kind of XXZ, yes?
I don't know it's XXZ,
then,
but
not XXZ, but if you have sausage, I don't know whatever.
Yeah, in the O and Grossnever, for example, you have two periods. Yeah.
Two periods, yes.
Yeah.
No periods.
Yeah, also. Yeah, sometimes you have some exception. You have one period plus one exceptional singularity. This can also happen. Yeah, here I focus only when you have just equally spaced plus one additional non-perturbative term. Yeah. Okay, and then at the end I will conclude. So definition of the ON nonlinear sigma model as a quantum field theory. So it's nice to emphasize that we could be related to QCD because this theory is really quantum field theory. You have a perturbative expansion. You can start from a Lagrangian. So here you have a field which has n component and lives on the circle. Which has global ON symmetry. So you can pick any of these ON charges, and then you can couple to this conserved charge a magnetic field. So this is your Lagrangian. You have a bare coupling, yeah? And then it's a bit tricky with this term, it's the Euclidean version, because it was constructed exactly such a way, such that if you calculate the Hamiltonian will be shifted by this charge times the magnetic field. So what you could do perturbation theory. So you just pick your vacuum, you expand one of your fields because you live on the circle. In terms of the others, you plug back the Lagrangian, the action, and then you make a path integral for this n-1 variable, and then you define the free energy density, and this is the observable we are interested in.
Is it integrable? No, yes.
It's integrable. Yeah.
Integrable.
Yeah, otherwise I wouldn't be able to do anything. I wanted to
Well,
emphasize that.
Perturbation then.
But we could forget about integrability. So this slide is exactly about that. But even if it's not integrable, this is the procedure which works. So I could just do perturbation theory. I do dimensional regularization. I introduce the running of the coupling.
I mean,
Yeah.
if you do a perturbation, you don't need integrability.
Yeah, but why do I need? So indeed, so just to make one point, so this free energy density can be related to the previous quantities I already introduced by a Legendre transform. So rho and epsilon rho can be obtained in this way. Yeah, but forgetting about integrability, you start to do one loop, two loop calculation, and then that we did with Grisha actually, this two loop calculation. And then we calculated the free energy up to 2 loops, but it's so complicated. So nobody ever actually managed to go higher order. Maybe they were not so much interested in. But it's indeed impossible to go higher order, so we need integrability. So question how integrability actually can help to expand this, this free energy. So this nice insight came from Dima Volin. Actually, he figured out a very clever way how to expand this integral equation we are talking about, because I already introduced epsilon and rho, you remember, and then this is just a single integral equation. So what Dima figured out was that instead of using this rapidity density, it's better to use the resolvent, which is analytic everywhere except on the real line between b and minus b, and the jump is this chi. Clearly the density what we are interested in is just the residue of the resolvent at infinity. Okay, so this is one side of the problem, and it's nice to have the Laplace transform, because in order to express the energy density, it's related to the Laplace transform of the resolvent. And now the insight was that let's just imagine this this resolvent, and there are 2 domains where you can parameterize this function in a complementary way. So around origin, we know that it has this cut structure. So we just make an ansatz in terms of the C coefficients and the square roots. In more general cases, you could have also log. But in this particular, I'm just explaining O4, you do not have any logs. So this is a nice parameterization which is valid around the origin. On the other hand, because we are making a large B expansion, we could focus on the region, edge region, close to B, how the function behaves there. And then here you can use this Wiener-Hopf method, what I will explain later. And you can just solve the integral equation when b goes to infinity, because it's just on the half line, basically, and you got the solution explicitly. Okay, this is the b independent part, and then you just parameterize the b dependence, an expansion around s goes to infinity actually, in some unknown function. And what is kind of magical, that they have a kind of overlap. So in between, you can exploit the fact that they describe the function and its Laplace transform. So you can just take, say, this form and expand around the edge, do the Laplace transform, and then compare the equations for C and the Q. And then that part, what we know actually will determine part of the C, which determines some Q's, which then determines the C's. So this is a closed system of algebraic equations that you can solve. So using this solution, once you solve them, then you can express rho in terms of this already calculated C guys, and then you can calculate also the energy density in terms of these Q's. So that was Dima's idea, Volin's idea, and then it worked very nice. So what do you get? If you really do the calculation, then the result, for example, for this rho, which is we removed some normalization factors, so it starts with 1. And the coefficient you will see, contains either this log 2, some powers of log 2, and also odd zeta functions. And then, of course, if you go higher and higher orders, then every term can appear which has exactly that transcendentality, or lower. So you have a bunch of growing number of terms, but this is how you can go higher order in the perturbation theory. And of course, you can check the first few orders is the same like.
So what was A small?
A is.
Look, okay, I see.
And then you could do the energy. And then Volin did this calculation for he calculated his computer 22 coefficients, and then later it was revisited by Marino and Hreisch, and they calculated 44 coefficients, and then we calculated 50 coefficients, and then, but still it was not really enough to see the non-perturbative part. I mean, you could see quantitatively, but qualitatively, but not quantitatively. Yes, the physical observable, which is related actually to the Lagrangian calculation, is related to, to the ratio of epsilon divided by rho squared in the running coupling. And this is the running coupling, what you would get if you would do a perturbation theory in the quantum. So this is somehow the most physical observable, what we can calculate. A bit surprisingly, this log2 disappeared, only odd zeta functions. And then you could calculate many terms, and then, but, well, they are not very impressive. But I can't stand to mention that actually we calculated with Grisha that term, I think. Yeah. But the previous term was very important, and this calculation was done by Hasenfratz, Niedermeyer, and Maggiore. And the reason they wanted to calculate, because if you do the calculation in perturbation theory based on the Lagrangian, then you would do the calculation in terms of age divided by the dynamically generated scale from MS bar scheme, for example. However, in the TBA, you formulate everything in terms of the infrared data, which is the mass and the scattering matrix. So this integrable calculation will provide an expansion in terms of the ratio of H over M. So comparing the two calculations, you can actually relate. What is the relation between the mass and the scale? And then the explicit relation is here, yeah, which actually was first obtained by Niedermeyer numerically for the O4 model, which was just this, and he got a number for 10 digits, and he looked at it, and then he said, well, it's 8 over E. But we will do some of the similar tricks here, but with more digits, actually. And maybe also I mentioned that if you would do the same calculation for QCD, like to tell what are the hadron masses or the glue ball mass in terms of the QCD Lagrangian parameters, then you would win $1 million prize. So, so it's an important question. Okay, but now we have lots of coefficients, and then what we can read off from them. So analytically, not so much. And then 50 coefficients were not enough. So what we did, we realized if we would like to understand non-perturbative corrections, then it's enough to know this coefficient numerically. And then, so what we decided to calculate very high precision, like 7,000 digits, and then we calculated like 2,000 perturbative coefficients. We calculated it for this rho, epsilon, and this physical observable, we get like 1,400 coefficients. And then the first thing you realize, if you look them, you can realize actually on 20 terms already, that they grow factorial. Okay? And this is the factorial growth. So if you just remove this factorial growth, then it goes to a constant, actually alternating constant, and then some 1 over n correction. But you would like probably to see how precisely you can tell what is this number is. And then for this, what you do, you can, for example, if you go for that number, you can make this even combination of these two guys. And then what you see, the corrections are like 1 over n, to this constant. And then there is this nice trick of Richardson transformation, which from this series what you have here, you just need a new series, and the correction for this new series, you basically kill that term here, so the correction is going to be 1 over n squared. And if you do it many, many times, then the correction is like 1 over n to the 100, say. So you can really measure precisely these coefficients. Actually, subtracting that one, you can measure also the others. And here I'm just showing with really working that many digits, how precisely you can calculate it. So you can calculate for 200 digits that guy, for example. Of course, that many digits will be enough to, to guess what is it in terms of 8 and e or pi or whatever. So, question, what can we do this exponentially growing coefficient? And the idea is the Borel transform. But I would like to motivate a bit this Borel transform in the path integral language. So we would like to calculate, say, this observable in the path integral, in the O4 model, and we should think a bit that performing this path integral in 2 steps. First, we perform the path integral for a given action, and then we integrate for that particular value of the action. Okay, so we are performing in 2 steps. So in performing just the path integral for a given value of the action, we got a function which is basically is the Borel transform. So in the perturbative sense, it has the same perturbative expansion, except is divided by n factorial. So although the original perturbative coefficient was growing like factorial, after the Borel transform, if we just calculate that piece, this will be convergent. So if they will be convergent, then we can ask where are the singularities, and we try to analytically continue on the complex plane. So to find the singularities, because we can easily construct with 2000 term this Borel function, you can just make a Paddy approximate. So if you make a Paddy approximate, you will see something like this picture. So you will see a condensation of poles on the negative real line starting at -1 in the Cn variable in that function. You will see a pole at 1, and then you will see another cut starting at 2. Actually, there are higher cuts here and also higher cuts there. So this is the analytic structure, and now we would like to perform this last integral. But this last integral should go actually on the real line. If we were in a model when there are no singularity on the real line, then we could easily calculate it, and this means this is a Borel summable theory. But this theory, this O4, say, is not, because you see there is a pole here and the cut starting here. So we have to decide where to integrate. And we could integrate a bit above, or we could integrate a bit below. Of course, there is an ambiguity here. And then we can just ask, what is the ambiguity integrating a bit above or below? And you will see, for example, a pole will actually result in this non-perturbative term. So the non-perturbative corrections to our observable are related to the singularities on the real line on the Borel plane. Okay, that's the message. So if we would like to calculate this physical observable, then it's not unique. We could integrate above or below, and we have to integrate this analytic continuation of this Borel function a bit above or below. Actually, what we wanted to do, we wanted to perform these integrals and compare to the physical value, but we know the physical value because we have an integral equation. So we can just take the integral equation and solve numerical. But in order to get a good analytic continuation of the Borel function, we actually used conformal mapping. So what we did, so this is the analytic structure of our function. And then there is an easy way to calculate a transformation which maps the whole complex plane except these 2 cuts on the unit circle. So if you use this conformal transformation, then the whole complex plane except the singular parts will be on the unit circle, and the previous expansion, which had the convergence radius 1, and then it was not convergent here, it will be convergent on the whole unit circle. So it's good because then we could make the integration there very nicely. So this is what we did. We used the conformal mapping. We fixed the first, I don't know, 2000 perturbative coefficient in this Borel variable, and that we plug back to this integral, and then we calculate it very precisely. So this is exactly the best we could do from this perturbative data. But we wanted to compare to the solution of the TBA. So what we did, we just parameterized the unknown function with some Chebyshev polynomials, and then we solved the TBA equations numerically, and we got in the O4 model the ground state energy density for 30 digits. And then we compared what we got here. And first of all, depending on plus minus, we had this ambiguity. We choose a plus, and then we got an imaginary part. And of course, the solution of the TBA was real, so it's really a bad answer. But nevertheless, calculating this, say, lateral Borel resummation by integrating here in this, after the conformal mapping, we got a very precise expression for which we could fit this function, and we could fit this coefficient very precisely. So this is something which came out from the perturbative series, but it cannot be physical. And then we compared also the real part, and then, because naively you could say, why don't we just take the real part? Integrate above, below, divide by 2. But if you do so, you will see that there is a discrepancy between this Borel resummed integral and the numerical solution of the TBA, which goes e to the minus 8 over alpha, very, very non-perturbative. And we could even fit these two coefficients.
So this is because of overlapping cuts?
Yes.
Because of what?
Because we will have later cuts here, and the cut will have a cut. I will show this. So now the question is that how could I get these informations, what we measured here, directly from the perturbative series? And this is the question I would like to answer now. So that in order to solve, we should a bit understand our function on the Borel plane. So we had, say, the original function, which has expansion coefficient, this Sn. And then we would like to go to the Borel plane by dividing the perturbative coefficient by n factorial, such that this series has a finite convergence radius. Okay? So this means that C coefficient will have a constant asymptotic sin n, but it will have an alternating part, and then it will have a non-alternating part. And we have this constant, and additionally we have corrections, 1 over n times n minus 1. And what we could do actually to sum up these guys one by one. So let's focus on, say, this alternating part. So if I just, that's the expansion of the asymptotic coefficient, let's keep the first guy. If I sum up, I will get a term, which is actually a pole on the Borel plane, at minus 1 with residue p minus. If I take the next one and I sum up, I will get a term, logarithmic cut starting at minus 1, multiplying with this p0. If I calculate the next one, I will get a logarithmic cut multiplied with a function multiplied with 1 plus t. So if I do this calculating all these guys, I'm reconstructing a function in 1 plus t which multiplies this logarithmic cut. So in this resurgence terminology, we denote this function multiplying the logarithmic cut as delta minus 1 in this case of the original function, which is called the alien derivative, which is related to this perturbative coefficient, the asymptotics of the original perturbative coefficients in this particular way. So this basically the alien derivatives tells you on the Borel plane what is the jump of the function on that cut. So there is this alien derivative at -1, which is non-trivial. There is an alien derivative at 1 and 2, and there will be other cuts later. So that now we played this game. So we just so this is, I guess, the asymptotic value of this Cn when n goes to infinity. Using this Richardson, higher order Richardson transform, you got a number like this. And then you ask, so what is this number? And it's almost 8 over E, but actually János Balogh conjectured what it should be, and indeed we checked this was the same number for 150 digits. So it was a bit guesswork now, and then you go to the next, and you see if you divide by the leading guy, all other has the similar transcendentality as we had before, that just odd zeta functions. So then there is a nice calculator, easy face on the web. So if you have a number, just you ask what in our combination of zeta functions is this number. So you can reconstruct all this alien derivative, say, of that function. And then similarly, you can clearly see that here you have only a pole singularity, and then you can calculate this second alien derivative of the function, and you can fit like 10 coefficient analytically, and then you have like 60 coefficient numerically.
But
So
this procedure only allows up to 5 operations or something like that. So it only allows up to 5 operations, I think, this website. So
What do you mean nothing?
Yeah.
Otherwise you have to pay or?
no. You give 10 digits, and then it will find something that involves fundamental constants and 5 operations at most. If your number is exceedingly complicated.
At one point we had to use just a brute force implementation of this in mathematics, some least squares thing or whatever. I think it's
actually
not
there is a
complicated.
built-in function in Mathematica which can do it. That's just we learned after. No, not
No,
rationalized.
you're just looking for a combination with the rational valued coefficients of some given numbers. Then basically I think you just guess the common denominators, or actually you're looking for integer combination. And then that's it.
No, I don't remember now what is this nice function, but it actually checks linear independence on a basis, and you can tell what is the basis.
I also forget the name, but it's
Should be PCQL.
find dependence.
PCQL. There is an algorithm which allows you to define. So if you give basis of irrational number.
Yes, but in Mathematica you just specify that what is the linear dependence of sometimes zeta 3, sometimes zeta 5, and my number and 1.
With integer coefficients, most important.
And 1, and then it gives it.
Yeah.
So if we know actually these alien derivatives, we know that this is a logarithmic cut, and then what functions multiplies the expansion of the function of this logarithmic cut, we can actually plug back to this lateral Borel summation, this integral, and then you will see it will exactly give, a pole will give such a non-perturbative correction. And the next cut will give that non-perturbative correction. And these guys are going to be imaginary, and you compare your imaginary result of this lateral Borel resummation and exactly the same numbers we measured from the discrepancy you will see. But what is the origin of this real ambiguity? Yes, that's the next.
What means next cut? Do you have branching points and no cut?
Yeah.
in between, or-
So there are more cuts here.
And you put them on top of each other, that looks strange to me.
Yeah, I wanted to emphasize that it has actually 2 origins. So the original coefficient could have a cut, or that function could have a cut here, but you remember we identified the function which multiplied the logarithmic cut here, but that function could have also a logarithmic cut. And that logarithmic cut of that alien derivative, that function, shows up there. So that's why I wanted to emphasize that it has two origins. One, it's a logarithmic cut of the original function, but also a logarithmic cut of the one which multiplied the logarithm. So it's the cut of the cut which appears here, and if you go on, there are infinitely many. So there is a nice way of keeping track of these guys, and then that's called the Stokes automorphism. So you could compare what happens if I integrate a bit above and below, and you can take the difference, and then you can ask what is this function. And then what is nice about this alien derivative, so you can express the difference between these two integrals in terms of the alien derivatives of this function. So there is an alien calculus, and then this is an exponential form what appears here. This is called the Stokes automorphism, which is basically the exponent of all the alien derivatives. So you have to know all the singularities on the real line, and you have to calculate all the jumps and the jumps of the jumps and so on, because you can have many alien derivatives and higher powers. So in many cases, and then that's probably all these physical applications, the correct value, what the physics should be, is the median resummation, which means you have this automorphism when you switch from one side to the other, and then you just take the square root of this automorphism. It's like stopping in between and then integrating basically on the real line. So this calculus tells you that what exactly you just actually make 1/2 because you are taking the square root. So this is the combination you are supposed to integrate. And the claim is that this is free of ambiguities. So if you would integrate the first function, it has a cut. So there is an ambiguity if you integrate above or below. But that ambiguity, which is of leading ambiguity, which is of size e to the minus x, is compensated by that piece here. So the whole result eventually is free of ambiguities. So in our particular case, if we would like to see what is the median resummation of our perturbative series, we should calculate all these alien derivatives. And then we already measured from the asymptotics this delta 1 and delta 2, but we should also measure, say, delta 2 square. So we measured from the asymptotics this delta 2. I told you we calculated some coefficients here. Yeah, and then numerically I know like 60. So I have to analyze the asymptotics of that function. This is the cut of the cut. And then we did this analysis. From the asymptotics, we could find the first two coefficients. Later, we could find it analytically. And when we plug back to this formula, we indeed get a correction e to the minus 8 over alpha. And this is the same what we have seen in TBA. So that's exactly what I explained. So we compare this with TBA, and they are really there. So what does it mean? It means that probably this TBA, the physical observable, has this transseries form, which starts with the perturbative coefficient, and then there is a first non-perturbative term, and a second non-perturbative, and so on non-perturbative terms, and they are all related in the sense that the large n asymptotics of the perturbative series will determine the non-perturbative correction. Actually, it also determines that non-perturbative correction. It's a subleading large n behavior. And then actually at this order you have the large n asymptotics subleading large n asymptotics of the perturbative coefficient, but additionally you also have to analyze the asymptotics of that part. So here we calculated the first few terms of this trans series, but eventually we would like to calculate all of them. And then we didn't believe it's possible, but we managed to do it actually in the last year. So how much time?
10, 15 minutes. 10.
Okay. Yeah. So we did it for the O4 model, and then we wanted to repeat all this machinery for O3. And then a slight, actually very similar, slight difference that we don't have cuts on the negative real line, only on the positive. We have a pole, we have this cut starting here. So we repeat exactly doing the asymptotics of the asymptotics, and then we came up a form what the TBA result should be. And then we just measured, so there was an expected real deviation from a similar arguments, what should be the deviation between the TBA and then this summation of the trans series, I mean what the perturbative part determines. And then it should have been that form, and we measured numerically. And what we found that it's completely different. It starts much earlier. This idea that the perturbative coefficients determine the non-perturbative corrections is not true here.
So that came from comparing with the numerical solutions?
Yes. Just from numerics, we could see that there are terms here. We could even fit this coefficient quite precisely, because in the O3 we had like 50 digits for the TBA. And I didn't talk anything so far about the origin of these non-perturbative corrections, but it is believed that in the ON models they are related to renormalons. But the O3 model is very special because that's the only model where we have instantons. So most probably this is the contribution of an instanton, and then somehow the perturbative series doesn't know about this instanton. So it would be very great actually to do a kind of instanton calculation and try to calculate all these coefficients, because we know what should come out. So now I would like to derive this trans series and all the non-perturbative correction directly from the integral equation. And it's very technical, so probably I don't go very details. I will tell you just the ideas. So the first idea is we would like to use Fourier transform. So this is the idea of this Wigner technique here. So if the integral will go, would go from minus infinity to plus infinity, then we could just use Fourier transform. But it goes from minus b to b. And this is so the unknown function lives only between minus b, and the source term, which is cosine hyperbolic n theta, it also lives only there. So the idea is actually to extend the integration, and the price we have to pay, we have to introduce like unknown functions. But this unknown function will be non-zero on the left, and that guy will be non-zero on the right. Okay? So now, because it's already defined on the whole line, we use the Fourier transform and invert the kernel in Fourier space. And this is a very important problem here, that it's a Riemann-Hilbert problem, that you have this function here, the inverse of the kernel, and you would like to factorize into two terms, one analytic on the lower, the other analytic on the upper half plane. And the reason you would like to do it, because these unknown functions are defined only in just half space, so their Fourier transform will have specific properties, analytic on the lower, on the upper half plane, if you shift them accordingly. So what you do, you just go to Fourier space, and then you shift some functions, and you write in Fourier space that integral equation, you multiply with one of these functions, and you try to separate the parts analytic on the lower and the upper half plane. And there is a projector, how could you could use it, and then if you project, for example, on the minus part, then you will get an equation for this unknown function, which is basically L and R, the extension of this function. And once you determine this function, you just plug back into the other one, and then you can calculate this observable. So that's the idea of this Wigner technique. But in this solution, it's not clear where these non-perturbative corrections are coming from. So you have to investigate a bit this integral equation.
Does it work for any B or only for large B?
You're producing an asymptotic
Yeah, sorry.
Yeah, that's what it was, yeah.
No, it works for any B.
Any B, yeah.
It works for you could solve this integral equation numerically, and then it works for any B. But why is it particularly useful? Because you can make this large B expansion. What I will show now. So after some redefining some function, you can bring the integral equation into this form. And then originally this integral projecting on the analytic lower and the upper half plane went on the real line. But the kernel, what is related actually to the ratio of this, in the factorization of the kernel, G plus G minus, you can introduce the ratio, yeah, and this appears as integral kernel in this integral equation, which goes on the real line. So what matters, what is the analytic structure of this alpha? And then because it involves this G minus G plus, it is singular on the upper half plane. Actually, it has a cut starting from 0, and it has many, many poles, equally spaced poles on the imaginary line. So you can just deform your contour, and then you have to be careful because the cuts are exactly on the poles, so a good idea actually to deform the cut a bit away. So you will have an integral here, but here the function, actually the jump of this function is a meromorphic function there, so you just integrate the jump, and additionally you add the contribution of the poles. Exactly the contribution of the poles will give the non-perturbative information, and the integral of the jump of the function on this ray will give the perturbative information. Somehow it's very nice in all the models that you can introduce a running coupling such that you have an expansion in the power series expansion of this coupling. Because in some models you have also log B terms, but in this running coupling this disappears. Yeah, it's a technical detail. So the final, yeah, there are many technical details, but at the very end you can write an equation, for example, the residue, this is the unknown residue of the unknown function at the pole positions. You can formulate a closed system of equation including a basis, what we introduce these A functions. In order to get your function, you have to perturbatively solve the perturbative part of this integral equation, and then evaluate some moment of the perturbative solution, and then modify a bit, shift a bit, and this appears in this equation. But it's irrelevant for the solution, how you get it. What is important that everything can be expressed in terms of these basic blocks, these A basic blocks, and these A guys are nothing actually but the perturbative part of this observable. Okay. So let me just show you the outcome for the O4 model, for the basic observable, the energy density. So if you go through the solution, you will find that it starts with this basic building block A11. That is the first non-perturbative correction explicitly calculable, and all higher perturbative corrections can be written in this A basis, with some residues which are called Stokes constants in this language. Now you should remember that from the integral equation, every higher observable can be expressed in terms of this basic one, A11. And A11 was the perturbative part of O11. So this is what we calculated as the energy density using Wolin's method. So we know A11 up to 50 order analytically, 2000 orders numerically. But plugging back to the integral equation, Then I can calculate chi1, I could calculate f, chi alpha. So I can calculate all these basic blocks perturbatively, A and M, just from A11, what we already learned from volume. So I have these basic building blocks to any order I want. I just show here the first few guys. It looks like this. So if I spell out the first few terms, for example, in the O4 model, this energy density, it has the perturbative part of volume. The first non-perturbative part we have seen already numerically. This is a pole. But now what we observe here, this was the first alien derivative. We calculated the first few terms, but we know them now explicitly in terms of this A basis. So any orders, we could calculate 50 orders analytically, 2000 orders, I know this function. And then we know all the higher functions actually. So there are higher cuts, and they all come where the kernel had poles. So we exactly know the non-perturbative terms, and we know all the jumps from this form. So this result is uniquely defined, and this is free of ambiguities, because this is, we showed that this is basically the median resummation of the perturbative part. So the perturbative part determines completely this whole series, and it's unique. And in the O4 is the same like the TBA. In the O3 it's not. So it's still missing that part. So let me just conclude and summarize. So it was nice to have this integrable description, because otherwise from Lagrangian perturbation theory we wouldn't be able to calculate that many terms. So here we used Wolin's method, we could calculate 2000 terms, and then we could play this numerical resurgence. We could, from the asymptotics, we got the analytic factor on the model plane. We could identify the poles and cuts, and we sort of understood how they will appear in the physical observables. Yes. And what was interesting that not only in the O4 model, actually for any ON model, when n is larger than 3, then the perturbative series determined all the non-perturbative information. However, in the O3 model, it was not the case, because there was this extra correction, which might be attributed to instantons. So if somebody is experienced in doing instanton calculation, it would be very nice to calculate this term. Yeah, so it was also nice to get this analytic result in terms of this A basis. So it is using this A basis, which can be calculated from the energy density. Using this differential equation, we can express all the observables. So we can express the generalized observables, we can express the boundary value of the field, and depending on the application, it could be the capacity of this disk coaxial disk capacitor, or it could be the Godin-Young model, or we could calculate, we haven't calculated yet, but we could calculate in the statistical models all the non-perturbative corrections. Yeah, so okay, yeah. What is not clear, and it's very interesting, I told you these higher saddle points probably are related to renormalons, and the renormalons in the perturbation theory are diagrams. Usually, So if you do perturbation theory, then non-perturbative corrections could have two sources. So one of them is the instantons, and you can see the effect of instantons that if you go higher and higher order, then you have more and more Feynman diagrams. So then it's related to instantons. So your perturbative coefficient can grow because there are many diagrams. But renormalons, in the case of renormalons, they grow because there are specific diagrams which themselves, one particular diagram can grow like factorial. So those are renormalons. And then it's not clear in these models whether they belong to renormalons or instantons. So, thank you for your attention.
so we have time for one or two questions.
Yeah, so this is extremely nice. I got a little lost in the last technical part. So in the beginning you had this double series in 1 over b and exponential minus b with coefficients. So do you manage to get a closed form expression for the coefficient?
Yes, sort of.
What was sort of?
So the claim is that if we can calculate, say, using this Wolin's method, the perturbative coefficients of the energy density, okay, then of course we don't have a closed form for that perturbative coefficients, but we can calculate the first 50 analytically. And they all have these odd zeta functions. And then if you go to, say, 50 order, then every combination of odd zeta functions up to that transcendentality can appear. So they grow like more faster than factorial. So you cannot write them really down explicitly. But on the computer, Mathematica can calculate. So if we consider them as input, then I can tell all other higher C and M coefficients in terms of those.
Could you explain again what actually didn't work in O3 model? What did not work in O3 model?
Yes, so in O3 model, so the question, does the perturbative series determine the non-perturbative correction? And there is a procedure which I could rephrase that if you calculate the perturbative corrections, then they grow asymptotically. So you have to do a resummation. Let's do Borel resummation. So there is an ambiguity. Let's kill the ambiguities. What is the minimal set which kills all the ambiguities? And then you could say, is it the physical answer? And in O larger than 3 it is, in O3 not. So there is another non-perturbative.
My question is slightly different.
Yeah.
If when you go to Borel plane, do you see Borel singularity corresponding to this additional contribution which you was mentioning in O3 model? Do you have additional? The answer will probably yes. You do have.
Yes, you have.
Okay, so which means that if I'm studying with Borel integral, there is contribution from this particular pole which give you contribution which you attributed to discrepancy.
Yes.
But does it mean that there is discrepancy because you use wrong prescription for integrating this particular pole? Because you were using principal prescription for Riemann pole.
No, it's not. Because from the TBA, so maybe, let me see.
No, if there is Borel pole making your integral, this Borel pole will give you contribution. Now the question is what you call discrepancy. That you're not able to describe this contribution or it's missing, I didn't get.
So I can calculate this quantity in two different ways. So one way directly from the Wigner solution of the TBA. Then I can see on the Borel plane that there is this there is a singularity which gives the instanton. Okay? I could get the Borel plane just taking the perturbative result and analyzing its asymptotic. Then I can.
You cannot.
I cannot. It's not there. It's something which is not in the perturbative series, in the asymptotic series. But in the TV, solving the TV, I can see there is an extra pole.
But then it's contradictory to what you're saying that it could be instant. Instantons are seen at the level of perturbative expansion, as you said. It is, maybe I misunderstood. If these are real instantons, instantons will appear as n factorial divergence of perturbative coefficient.
Yeah, Yeah, actually, in general, usually the instantons knows about each other, and the perturbative series knows about the instantons. Yes. But here, in other models, we know in all n larger than 3, there are no instantons.
So that's
but the perturbative series knows about the saddle points, it seems, but there are no saddle points. So what are those guys? Those are renormalons, but renormalons, they don't have a semi-classical meaning. So it's very puzzling here. In quantum mechanics, they usually do this instanton stuff, and then they are all related very nicely connected only instantly. It's a quantum field theory, and it behaves completely different.
Okay, maybe one last question.
So, is it in principle possible to extract instanton contributions from saying that this is the contribution of instanton of charge 1? This is contribution.
I don't know if it's an instanton. I can tell you there is a non-perturbative contribution in the path integral. I can tell you what is the value of the saddle point if it's a saddle point. I can even tell the fluctuations. What is if you expand around that saddle point and you perform the perturbative expansion, I can tell you all the coefficients, but I don't know if it has that origin.
Well, but you know, because you know action of the instanton. You know the value of the action. The value of action of the instanton defines position of the barrel pole.
Yeah.
If you know that your additional contribution sits exactly and the contribution is put into the action of the instanton, this is the instanton.
Yeah, but nobody knows any instanton in the presence of a magnetic field. If I switch off the magnetic field, I know there is an instanton. Yeah. So it's good for future.
Okay, good. So let's thank Zoltan again. And